Bonjour, merci Mohamed pour m'avoir invité à parler dans cet événement. Je vais parler en anglais parce que je préparais ma présentation en anglais, mais vous pouvez me faire des questions que vous estimez en français sans problème, et n'importe quand, et n'importe où. Well, without more dilation, I will talk about inaccurate information, artificial intelligence, and quantum computing. The thing is that we are going to need to reason with inaccurate information. Reasoning with inaccurate information means reasoning with a lot of things, because inaccurate information has lots of interpretations. On the one hand, it may happen that the information available is incomplete, and we have to reason with this incomplete information. Also, in many cases, the information available is not sufficient to make a categorical decision. Sometimes the available information we handle is not exactly true. Also, the information we use is usually imprecise. And we can also take into account that normally the real world is non-deterministic, so intelligent systems are not always governed by deterministic laws, and that means that general laws are not always applicable. Also, if we refer to the model that we build, because remember that the building expert system is building a computational model of intelligent behavior, we can say that our model is often incomplete, and there are many phenomena whose cause is unknown. But the most amazing thing is that the lack of agreement between experts in the same field is frequent, and both circumstances make it difficult to include knowledge into a rule-based system. We are going to explore the categorical models for reasoning, then go to probabilistic models of reasoning. Then we will explore the quasi-probabilistic models. We are going to talk about the uncertainty factors and the theory of evidence, and also fuzzy logic. We will find all the classical approaches using a vectorial way of reasoning. And finally, we are going to introduce the quantum model for reasoning. But take a look at this transparency. In the classical world, the categorical models are inside. Then there is the probabilistic models that contains the categorical models. Then we can approach the problem from a quasi-statistical point. That means that we are going to use the probabilistic tools, but without an enough number of statistical significant cases, and then we are going to approach the problem from the fuzzy set theory. But in the quantum world, the quantum model is still by its own intrinsically inaccurate because of the Heisenberg's principle of uncertainty. So the quantum models are intrinsically inaccurate or intrinsically inexact, or whatever we want to say it. But no matter the model we are using, the results will be always the same. Let me first approach the problem from the classic categorical way. In order to describe a given domain, we need to describe the universe. And this includes all the possible facts, 1 to n, and all the possible interpretation or solutions that could be interpretations of our problem, which has the following manifestations. To define the problem, we need a function f, which is a logical function, which assigns the number 0 to a given manifestation if the manifestation is not a manifestation of my problem, is here but it is not here, or assign a 1 if the given manifestation appears in my problem. And the same for the interpretations. We have a function g that assigns the number 0 to a given possible interpretation of my problem if it's not a possible solution, or assigns a 1 if it's a possible solution. What is missing here is the knowledge that relates manifestations and interpretations. And this is called the function E. The logical problem is to find a transition between F and G through E. Let me show you a simple example. We have to describe a domain that has two manifestations that could be possible. Both manifestations are in the description of the domain. And then we have two interpretations that are possible in our domain. And then we have a set of rules. This defines the declarative knowledge of our intelligent system, and this defines the procedural knowledge of our intelligent systems. Now let's put a given problem to our system. There is not the manifestation 1 and the manifestation 2 is present. So making the appropriate substitutions in this logical set of rules, we can easily find that the solution to our problem is that the interpretation 1 is true and the interpretation 2 is false. But this is a very particular way of performing reasoning from a categorical perspective. We need an alternative categorical model to define in a more precise way the combination of facts. So we put in this previous case that I showed you before, the following situation: 0, 0, 0, 1, 1, 0, 1, 1, meaning that in the first column there is no manifestation possible, in the second column only the manifestation 2 is possible, in the column 3 only the first manifestation is possible, and in the column 4 both manifestations are possible. You have to take into account that these columns represent exclusive situations, or the problem has two manifestations, or it doesn't have the first and have the second, and so on. The same thing we do for the interpretation model, for the interpretation field, in which we have also the same thing. Then we can combine in all different ways the manifestations and the interpretations, so that what we have is what we call an expanding logical basis. We have the complex x1, y1, x2, 1, x3, 1, x4, 1, x1, 2, x2, 2, x3, 2, x4, 2, and so on. The expanded logical basis has all the possible solutions, of the possible combinations between interpreted manifestation and solutions to our problem. But a lot of them are impossible by knowledge, and they have no sense. For example, if we take into account rule 1, for the second interpretation to be true, then it's necessary to have the first manifestation. The question is, what is the second interpretation true? In E2 and in E4. But for E2 and E4 to be true, we need X1 to be true. And in here, in here, in here, and in here, X1 is not true. So these elements should be eliminated from the expanded logical basis. If we do the same with the second rule, we have to eliminate these two complexes. We have the rule 3 and apply the expanded logical basis. We have to eliminate this complex. And when we consider the fourth rule, we have to eliminate these three complexes. So the final result of applying our knowledge to our system is what we call the reduced logical basis that only includes those elements that, being possible, are also permitted by the knowledge we have on the system. The process then starts with an expanded logical basis. We apply the knowledge to reduce this logical basis, and we define now our current problem. The problem is given by the complex of manifestations x2, which is associated with in the complex x2 y3. So our solution is y3, which individually speaking is that the interpretation 1 is true and interpretation 2 is false. But let me think a little bit about that. It is clear that uncertainty appears spontaneously even when we consider categorical models. Assume that we have now a different problem. It's a categorical way to deal with. We have the manifestation 1 and we have not the manifestation 2. Then we have the complex x3. But in the reduced logical basis, the complexes associated are x3, y2 and x3, y4. So that gives us two solutions. Individually speaking, y2 is always possible, and conversely, y1 could not or could be a solution of our problem. So the interpretation is that y1 could be a solution of or could not be a solution, and y2 is for sure a solution of our problem. Deal with this approach, we are interested on knowing which of the two situations is more likely. For that, we use Bayesian methods, in which the simple equation for the Bayes theorem is this one, that we can generalize, but in order to be practical, we have to consider a set of independent items in which the conditional probability, that means the rules the corresponding rules, are defined as the joint probability divided by the probability of the event given. In our example, we need the joint probabilities, the whole set of joint probabilities, and if we go from data to solutions, we also need the total probabilities of the manifestation, but if we go from solutions to data, we also need the total probability of the interpretation. We have to make a thinking about that. Joint probabilities of elements that do not appear in the reduced logical basis must be zero. And this is very important because it makes consistency between the statistics and the knowledge engineering task. If we ask an expert from a given conditional probability for a given rule, and we express that in terms of conditional probability, if we then make a statistical approach, there must be some value for this rule. Also, to ensure mathematical consistency, the sum of the conditional probabilities of elements that share conditions must be 1. In our example, the conditional probability of interpretation 2 given manifestation 1 must be 0, since x1 and y2 do not belong to the reduced logical basis. Conversely, this conditional probability must be 1, since there is only one complex in the reduced logical basis, which is x2. And the sum of both conditional probabilities, like appear here, must be 1, since both complexes are present in the reduced logical basis. And this opens a very interesting perspective from the point of view of knowledge engineering. And obviously, categorical reasoning is a particular case of probabilistic reasoning. There are some problems with this approach also. Imprecision concerns declarative knowledge or facts, meaning that is a situation in which the fact by oneself is uncertain or is inaccurate. Uncertainty is a different stuff. Uncertainty concerns procedural knowledge of rules. If we express A implies B, imprecision refers to A or to B, and uncertainty refers to the arrow. But also there are other kinds of inaccuracy, like lack of knowledge, vagueness, belief, disbelief, and so on. Also, when dealing with knowledge, one of the main problems of probabilistic models is their own mathematical consistency. I know that will be shocking for you, but still I have to say it. If we have the probability of a given hypothesis given an evidence equals a number, so that this number belongs to 0, 1, the conditional probability of the negation of the hypothesis given the evidence should be necessarily 1 minus the previous value. That means that the same evidence is related positively with the hypothesis and with the relation with the hypothesis. And this never happens when we try to extract knowledge from an expert, because the knowledge of the expert is incomplete. He can say that if it assumes subjective conditional probability, or that, but the sum not necessarily is 1. So subjective conditional probabilities have been proposed for this problem. With that in mind, we can go through the model of certainty factors. In the model of certainty factors developed by Charles and Buchanan in 1975, I believe, they, by axiom, define two different measures of belief. They are calling increasing belief or increasing disbelief. Assume that we have one hypothesis with a given probability, and it appears a piece of evidence. If the evidence increases the probability of the hypothesis, then the measure of increasing belief is defined as an increment, conditional probability minus previous probability, divided by 1 minus the probability that we had before. And this is because they want to make the model consistent with the theory. If the new evidence definitely declares that the hypothesis is certain, then we have that pH given A is 1, so that as increasing belief cannot increase anymore, they have to divide it by 1 minus pH. But if the hypothesis, the new evidence goes against the previous approach, the previous hypothesis, then the increment is in the reverse side. Is a positive increment, then is pH minus the conditional probability of H given A divided by pH, which is for exactly the same reason that we had before. Then they resume these two expressions in what they call certainty factors, which is the difference between the measure of increasing belief minus the measure of increasing disbelief, which is a formal way to express the thing, because the certainty factor given one only evidence is or the measure of increasing disbelief or minus the measure of increasing disbelief. If the conditional probability given the evidence is greater than the actual probability, then the measure of increasing belief is greater than 0, and the measure of increasing disbelief is equal to 0. The same evidence cannot be related with the hypothesis and with the increasing of the belief in the hypothesis and increasing the disbelief. The same for the increasing disbelief. But if pH given E is equal to pH, that means that the evidence is independent of the hypothesis, and the belief does not increase and does not decrease, and the certainty factor is 0. But this is a very important thing, because we can approach the problem when we want to say, I don't know, in probability. It depends on the number of characteristics we have. One half, 1/3, 1/4, 1/5. But in certainty factors models, I don't know, is always said by a given a CF of 0, a certainty factor of 0. Then we can scale from -1 to 1 with a set of individual labels that assume several ranges of certainty factors. For example, impossible is a CF equal to -1. Sure is a certainty factor of 1. Almost sure is a little bit less, and so on. I don't know is I don't know, 0. Nothing goes go, or nothing goes against. Then we will use this fact. But we have also to take into account that certainty factors are different from the conditional probabilities. For example, assume that we have a certainty factor, which is the measure of increasing belief minus the measure of increasing disbelief. Assume a hypothetical case in which the evidence increases the probability, the conditional probability of pH, so it's greater. So in this case, we have the CF, if there is a mistake here, a CF, the H given E equal to minus B, H given E equals to pH given E minus pH divided by 1 minus pH. Since pH and pH given E are probabilities, it comes that we can develop this function in terms of the negation. See that we are not saying nothing about the concept of the conditional probability, but we can express that in terms of negation. And it comes that the certainty factor of H given E is minus C, a certainty factor of not H given E. So it's not the complement to 1, but is the negation. But the evidence doesn't come alone, and we have to assume or to presume that could be 2 or more evidences that are related with the same hypothesis. For example, we have evidence 1 that is related with H, with the hypothesis H with the certainty factor 1. We have evidence 2, which is related with H with a certainty factor. And the way of combining is this sets theory. Is if both are positive, is the sum of the union minus the intersection. In order to preserve independency. The same for the case in which both are negatives, and in the case of one is positive and the other is negative, to make the model associative, they have to divide that by 1 minus minimum of the absolute value of CF1, CF2. An important thing concerning that matter is that the propagation of uncertainty or the inaccuracy. Assume that we have rule 1 that says in natural language, if it rains a lot, I normally stay at home. So we can say that A1 implies H1 with a given certainty factor, where A1 is it rains a lot, and the certainty H1 is stay at home, and the certainty factor 1 is normally. If always I stay at home, the certainty factor should be 1. We have another reference rule, which is if I stay at home, I used to read a book. So we have that given H1, we can imply H2 with CF2. But now we have a problem. The problem is that it rains moderately. So the evidence we have is not exactly it rains a lot. It's something similar. It rains moderately. So the question is, which is the certainty factor of reading a book? Well, Sharif and Buchanan proposed the following equation, is that the certainty factor of reading a book, given that it rains moderately, is the same that it rains moderately times maximum of 0 CF1 CF2, where this is imprecision and this is propagation. Further to sum up what we have called, we need also to know how the logical combination of clauses in procedural knowledge are treated by the model. For example, if we have A and B, we use the minimum, and we have A or B, we use the maximum. With that, with these equations, this is all that we need to apply the model of certainty factors. Let's go through an example. We have a given problem in one system, a complex system, like could be, for example, a refinery, say something. And we have a given, the engineer has a given hypothesis. This is the knowledge he has in order to use for solving the problem. And this is the facts we have that define the problem. If you see that we have 3 different branches. Branch A, which is A1 and A2 or 3, A3 given to give H with a given certainty factor. Then we have another different branch, which is B, and we have a third different branch, which is C. The first branch is made by a set of facts and a conclusion. A conclusion that is not exactly true. So we have A1, if A1 is always true, and if E2 is true or E3 is true, then the percentage of credibility that we have in the hypothesis is 0.9. But we don't have this. We have something similar to E1, which I call epsilon 1. And we have something similar to E2, which I call epsilon 2. And we have something similar to A3. So which is the solution of this branch given all the evidence we have? We are going to talk a little bit later about that. The second branch is E5 and E6 to give A4 and A4 to give H. So that here there is a problem of propagation. The third branch is a problem which is different. Well, the second branch, we have also the real facts, not the facts we need. And so we have to define the corresponding inferentiality. In the third branch, we have the situation. So the problem is that we need to calculate the contribution of branch A to the hypothesis H, and if we made the calculation, we arrive to the following solution, which means that given the all evidence, the hypothesis is 79% true. Then we go to our solution and we say to the user that the hypothesis is almost sure. This is why the scale of the certainty factor is so important. Let me go one step further and to talk a bit about the theory of evidence, which is a difficult theory, but I'm going to try to explain it in a very simple manner. We have the frame of discernment, which is built from the set of the whole hypotheses that can be given in a given problem. And we have a given evidence that supports a given subset of the frame of discernment with a value S. The rest of the certainty, we could say, is distributed homogeneously into the frame of discernment. This seems surprising because in the theory of probability, this 1 minus S should be assigned to the complementary of the subset. But it seems that the main problem of this theory, the main issue of this theory, is that if we don't have any evidence, the measure of increasing belief assigned to the frame of discernment is 1. But when what given evidence appears with a value MA, this should be subtracted from the frame of discernment. So the reason is that we don't have any evidence, and then an evidence appears, and then we can concrete a little bit more our problem. There are two main issues: that the summatory of MA should be 1, and the measure of verosimility of the empty set is 0. The problem is that the evidences, like in the previous model, doesn't appear alone, and we have to have E1 and E2. The first approach for combining is the direct product of the corresponding measures of verosimility. So that is a problem. The problem is that when the intersection of these two subsets is empty, but still we have a value. In that case, it appears one thing that is called the degree of conflict. That means the inconsistency between the evidence that are being combined. The sum is always 1, but in order to obtain the real fact, we have to divide by 1 minus k. Let me put one example, a very simple example, just to illustrate the thing. We have one evidence that supports one subset, which is H1 and H2, belonging to a given frame of discernment, which is the same as this other frame of discernment, but I put subindex in order to point the evidence that is the supporting fact. We have H1, H2, and on the other hand, we have H2, H3, H4. The intersection between these two sets is H2. The intersection between these two subsets is A2. the intersection of these two subsets is A1, and the intersection of these two subsets is theta 1, 2, and the sum is 1. Then the degree of conflict is 0, because the measure of combining evidence is 0. And then it appears another different evidence that points the individual hypothesis in each one. Here there are two conflicts that appear. And so the solution, the final solution, must be evaluate the degree of conflict and to divide by the corresponding factor, so that we have the final probabilities of the different situations that appear in the model. Note that this means that the summation is always 1. There is an interesting thing in the theory of evidence, is that uncertainty is limited by two different factors that are called credibility and plausibility. If you go to the presidential elections, we used to hear the Popular Party can be between 17 and 21 seats in the Congress. Well, this lower number is called the credibility and includes all the subsets of the focal element. And the plausibility includes the measure of verosimility of all the intersections that are different to the empty sets, so that the confidence interval is the real uncertainty, which is no more an only number, an unique number, but is an interval between the credibility and plausibility. And some interesting cases can be obtained here. The credibility is always between 0 and 1. The plausibility is always between 0 and 1. The credibility is always less than or equal to the plausibility. The I don't know is credibility equals 0 and plausibility is equals 1. Yes is credibility and plausibility 1. No is credibility and plausibility 0. But there is a strange situation in which credibility and plausibility are equal, one to the other, but they are different from 0 or from 1. And this is a particular case. What we have in this case is the probability. The statistical probability is, in the theory of evidence, the situation in which the credibility is equal plausibility, and this one could be also 0 or 1, but in general terms they are different. In order to demonstrate that this theory is more general than this, let us consider the situation of the certainty factors theory that we saw before. We have the certainty factor of a given hypothesis given the evidence. If the evidence supports the situation is S1 plus S2 minus the product. But if we applied with the same spirit the theory of evidence, we obtain exactly the same result. So that means that the evidential theory contains the theory of the certainty factor. Finally, we are going to go through fuzzy logic, in which we need a controller, a knowledge base, a classification module, which classifies in linguistic terms a given parameter. We have the engine, the inference engine, and we have to decodify. Let me show you a given example. Assume that we are in a bank and we are planning to ask for a credit. The technician knows that if the project funding is adequate, which is fuzzy, or the project staffing is small, then risk is low. On the second hand, if the project funding is marginal and the project staffing is large, then risk is normal. And if the project funding is inadequate, then risk is high. So we have three different situations. We have for funding three zones, A1, A2, A3. Between this number and this number, in here, the situation is clearly A1. Then it starts to decrease. In the second label, we have this situation, and in the third label, we have this situation. Also, we have the same for the B parameter. And we have now a real case in which we go through the X label, we cross A2 in the value 0.2, and we cross A1 in the value 0.1. So the same numerical input has two different interpretations, A1 and A2, with the different fuzzy numbers. The same for the second situation. So that we have to say to do that now is apply the rules. The first rule said if X is A3 or Y is B1, then Z is C1. Let's explore slightly what does it mean. This part doesn't trigger because X is not A3. But this part is triggered because B1 Y1 is 0.1 B1. As we have an OR, we use the maximum and we make a projection on the C1 part of the representation. The same for this and the same for this. So we have to compose now three situations into one graph. And we have to calculate, in order to decodify the process, the area which is below this figure, which is made by a certain degree of membership with a classical center of gravity, and we obtain that the probability of getting the credit we are asking for is 67.5%. Finally, we go to the vectorial approach, which is simply to codify the symptoms and the solutions and the symptoms and diagnosis with conditional probabilities. This is in the other way. We have a toy problem, which is to combine the corresponding associated complexes with given numbers. We can pass to probabilities. But which is very important is that in vectorial reasoning, the position of a bit 1 means a given complex of interpretation or solutions, in such a way that we can make a very compact representation of the knowledge. If S equals to 5, meaning that X is 0, 1, 0, 1, then we have that. So the position is very important. First conclusion we have to take about this is that we can combine different properties of inaccuracy like relevancy or severity into one only framework in which simply the product of the corresponding values, 0, less, significant, a lot, critical, could be combined in order to obtain a good representation. So no matter the model, we should be capable of modeling inaccurate knowledge. Let me finish the talk with the quantum approach to deal with uncertainty. We are going to assume that in the resolution of a problem, the facts may be affected by precision, and nevertheless we have to use the rules of the knowledge base to obtain valid inferences. For example, we have the fact A, this strange A, which looks like A but is not exactly A. We also have the fact B, which looks like B but is not exactly B, and the question implies to be able to manage inferences with these two strange characters and this rule which is in the knowledge base. We are using a categorical representation, and we are going to assume that uncertainty is propagation of inaccuracy. A classical circuit that can represent one problem in the inferential domain is this one, A and B to give X, X or C to give Y, Y and D or E to give R. This is the corresponding quantum circuit, where these are Hadamard gates, which can put the facts into superposition, and these are control gates. The result of applying this is exactly the same, but with a given probability. We consider now the Bloch sphere, which is a representation of the quantum bit. In the Bloch sphere, the quantum bit 0 is on top of the sphere, and the quantum bit 1 is in the down part of the sphere. But we have to use spherical coordinates, so we can say that a given state which is imprecise, this is superposition, is a combination of a modulus, the angle theta, and the angle phi, which gives us the phase of the problem. So, we use this angle theta as a representation of the inaccuracy of the state. We can project this onto the zeta axis in order to obtain a solution of the problem of the inaccuracy. And we have to build a kind of Hadamard gates, but that makes superposition differently from Hadamard gates. So, thank you very much for your attention.